now we're going to step it up. My sort of avenue to introduce that is to think about the two kinds of exponential growth and decay equations that you've met so far. There are only two. There's exponential growth or there's exponential decay, right? What do they look like? What do the equations look like? If I said, say P equals, for growth, what would it look like? AE or P naught, whichever, doesn't matter. AE to the power of KT, right? Where K is your arbitrary growth constant proportionality factor that tells you how fast it's going up, right? Of course, decay works in much the same way, and we introduced this on Tuesday, okay? How does the equation change? What's the difference? It's a simple difference. There's just a negative, that's all. Okay? Now, very quickly, without, heaps of detail, what do both of these look like? What do they both look like? Well, this looks like this, right? And you've got your asymptote at the P equals 0, right? And this looks like the same thing but in reverse. Okay. Now, the questions we've been looking at have been couched in terms which deliberately allow these two to be sort of the equations you can use, and off you go, right? But the reason why I say exponential growth and decay ... question mark is because in many, many situations this is not the way things behave. And this is concerning, right? Because the whole point of doing exponential growth and decay is to say, aha, this is how things function in the real world. They do behave. Their rates of change are proportional to what their size is, or their quantity or value, etc. So this is rather a problem for us, right? To introduce a topic that is all about understanding the natural world. This is applications of calculus to the physical world. And then to say, sorry, most things in real life do not function like this. Okay. Now, do you remember what was the example I gave you when we were looking at decay? I looked at two examples. One was about temperature. Do you remember what it was? It was a fridge, wasn't it? And I pointed out to you the fact that they talked about the fridge and they said that the temperature of the fridge was, does anyone remember? 0 degrees. But we were like, that's not the temperature of a fridge. Fridges are, I think they're 4 degrees, aren't they? Right? Why did they do it like that? Well, I'll tell you the exact reason why. They needed it to fit this, right? If the temperature's 4, if the temperature were 4, this doesn't match. This doesn't match, does it? If I wanted, capital T for temperature, or I think it was H for heat or something like that, okay? This is not tending towards 4, it is tending towards 0, so they crafted the question in order to allow you to use these equations, okay? But the problem is, we want to be able to understand situations where this is not the situation. What if I was to change it to 4 degrees? How would that adjust things, okay? Now, therefore, to help you understand the way this works and see why this is a 3-unit type thing, extension 1 type thing rather than a 2-unit, I want you to consider an example with me. And as in many cases, I'm going to talk about a population, okay? So let me give you a few numbers, and then we're going to build all of the maths off that. I'll give you as few numbers as I can. Here are the numbers. 2,000, 10,000, 6,000. Okay. Do you believe I can build a complicated question off those 4 numbers? Just watch. Okay, so what do they mean? What do they mean? I should get another color. 2,000 is a starting population. I made it up from the size of the school. Okay, so there you go. When times 0, you've got a population of 2,000. That's where you're going to go. Okay, but suppose we're in an area where there are constraints, where there normally are, right? In terms of space, in terms of food, stuff that's running around that you can eat, okay? So therefore, let's just suppose the demographers know that this area that we're in has a population limit of 10,000. There's no way it could support more than 10,000 people in there, okay? At least not without destroying all of the natural resources and so on, okay? So 10,000 is what the population is growing toward, but it's never going to actually get there, okay? So this is our case. This is our limiting case, if you like. Now, one more piece of information. Suppose we started off with 2,000, okay? But after 3 years, we took another census or something like that, And we found there was a population of 6,000. We'd tripled. Okay. So now I have, off of these sort of 3 pieces of information, I've got 3 questions to pose to you. Okay. The first question is, can we find the population as a function of time? Can we model this in some sort of definitive way, like these, but we're already sort of alluding to the fact that neither of these are going to be sufficient. Okay. Can we get population as a function of time? Can we find the population change, that rate, how that's changing in relation to the size of the population? Let me say that again and let me ask if you can explain how I would write this. Can we find how the population is changing over time in relation to what the size of the population is? What should I put on the right hand side? What am I looking for? I'm looking for the rate of change as a function of the population, right? That's what I'm trying to connect it to, right? I don't want it in terms of time, I want it in terms of how many people are there, right? So therefore I need a new function. Maybe we'll call it G or something like that. But it's not a function of time, it's a function of the population, okay? Because that's what we're expecting in exponential growth and decay. That there's some kind of proportionality between these two, okay? Last question. It took us 3 years to grow to 6,000 as a population. How long will it take us to go to a population of 8,000? There are my 3 pieces of information and my 3 questions. Pretty natural to ask. Now, I'm going to walk you through these in a second, but I wonder if you can get through any of this on your own steam. Have a think about it. I'll give you a clue. I drew these so that you could have a visual cue for what these look like, right? Drawing what you know is not a bad idea here either, okay? Have a shot. We'll see what we can come up with in a few minutes, okay?